Welcome back. We are still on the remedial journey. In our last session, we looked at systematic remedies as applied to the design and purchasing phases of the spiral. Now let's go to other phases of the spiral. Next is the manufacturing phase. The word manufacture as we use it includes first, manufacturing planning, the activities needed to put the factory in a state of readiness to produce. Second, production, the execution of the plan. Manufacturing planning comes first, and hence is the area which can gain most from early warning forms of quality assurance. The most fundamental need in manufacturing planning for quality is to assure the process will be able to hold the tolerances. Several approaches are available. First, the process capability study. We saw a simple example in the case of the shafts for the watches. Had the watch factory manufacturing planners made such a study as part of the original manufacturing plan, it would have avoided years of loss in scrap and sorting. In process capability studies, we measure the process indirectly by measuring the product. The product tells on the process. Second, we can assure process adequacy by direct measurement on the process. An example is the sterilization process used in pharmaceutical manufacture. We can use thermocouples to check the heat distribution of the sterilization chamber. That tells us whether all areas of the chamber can attain the minimum temperature needed to destroy dangerous organisms. The third approach is to discover the relationships of process variables to product results. Knowledge of these relationships is the key to high process yields and to improvements for the future. The above approaches for assuring process adequacy all require training in the diagnostic tools for quality. Our manufacturing planners are extensively trained in the technology of their processes, but they have only limited training in the diagnostic tools. To get such tools used requires bringing in those who do have such training, the quality specialists. But our experience in securing such collaboration has been poor. A better solution is to train the manufacturing planners in the use of the necessary diagnostic tools. Now let's go to foolproofing. The word foolproofing once carried a strong flavor of sarcasm. In recent years, we've come to realize that modern industry demands continuing attention, precision, technique, and so on, which cannot be sustained hour after hour by unaided human beings. One response has been a growing use of foolproofing during the manufacturing planning. In its broader meanings, the word foolproofing covers several approaches to reducing the incidence of human error. The oldest approach is aids to human muscles and senses. Planners quite regularly provide aids such as holding fixtures and locating indexes. They provide special containers to reduce damage during materials handling. Aids to human sensing now include extensive instrumentation and, more recently, such devices as closed-circuit television. That's right. Fail-safe devices are added to the process to prevent errors. They include alarm signals, all-clear signals, cutoffs, interlocks, and so forth. The most complete aid is the automated process, which senses actual product quality and then regulates itself accordingly. Another approach to foolproofing is countdowns and redundancy. These are used to provide early warning assurance prior to operations. A common example in factory production is setup verification. The first units produced are checked out for conformance to specification before running off the batch. More critical operations use more elaborate procedures. In pharmaceutical production, each batch formula or recipe must be weighed out by 2 registered pharmacists, each independent of the other. Procedures for surgical operations require that we count the tools, the sponges, and so on before the operation and again prior to closing up the incision. If something is missing, where is it? A similar practice is followed for cleaning or repairing certain critical large equipments. The procedure is to count the tools and components which go in and those which come out. There have been some cases of severe damage to costly equipments because of foreign objects being left behind by maintenance personnel. Countdown and redundancy are also applicable after production gets underway. One recurring question is, should the process continue to run or should it stop? In well-planned processes, the worker is provided with the means to answer this question. In important cases, we may build in some redundancy. We may require that an inspector concur in the worker's decision. In extreme cases, we go to extremes. In critical aspects of nuclear power plant construction, inspectors are stationed to watch while workers perform the operations. The workers sign documents stating that they performed the operations. The inspectors then sign documents stating that they saw the workers perform the operations. We can also foolproof the feedback to workers. These workers need to know whether they are conforming to specifications. The foolproofing principle involved is that performance of the work should convey a message to the worker. The message may consist of data on the product. The message may also come direct from the process. For example, a worker at a control panel pushes a switch and receives 3 feedbacks: the feel of the shape of the switch handle, the sound of the click made when the switch completes its travel, and the sight of a visual illumination of specific color and shape. A universal example is the audible beep given off when buttons on telephones or hand calculators are pushed all the way down. Some of them will even give him Mendelssohn. Foolproofing should also be applied to communications as well as to physical facilities or hardware. Communication on quality matters is extensive. Specifications, standards, procedures, test data. Foolproofing of communications has lagged behind that of hardware. The ingenuity is there. Foolproofing of hardware is often most ingenious. What is missing is the same level of priority. Some of the methods used to foolproof communications are identical with those used for hardware, but there are also some differences requiring special applications. A basic need in good communications is standardization of language. We saw in a building component case how 122 inches was communicated as 102 inches due to 2 different dialects in the drafting room. That little footmark got into trouble. Similarly, some medication errors in hospitals are traceable to dual dialects. Some older physicians still write prescriptions in apothecary units, but the younger doctors use metric units. The remedy for multiple dialects is standardization of language. Similarly, the remedy for multiple meanings of words is the glossary. The glossary can be supplemented by standard code numbers to simplify computer entry. Oral communication presents an added problem in foolproofing: how to shield the signal from the noise, literally. For centuries, military commanders have required their subordinates to repeat oral orders. This repetition assures that the orders have been heard. In the British Navy, during the 1830s, a key word was changed. The word for left had been larboard. The word for right had been, and still is, starboard. The opportunity for confusion is obvious. The word for left is now port. Still another approach is to use hand signals or other forms of redundancy. Here's a badge used by a Japanese company during a program to improve oral communications among workers stationed at a distance from each other. It reads clearly and in a loud voice. The job shop is very demanding from the standpoint of good communication. In mass production, the specifications, standards, and so on can remain fixed for months on end. A time is soon reached when the employees seldom refer to such information. It has been memorized. In contrast, job shop employees typically face frequent changes in materials, configurations, formulations, test requirements, and so on. Many job shop problems are traceable to errors in the information system. Planning for quality in the job shop should include special provisions to make clear in just what way does this job differ from all those previous jobs. These special provisions should include foolproofing to assure completeness and to minimize errors, analyzing the error patterns and then structuring improvement projects to improve the communication system. Still another systematic remedy in manufacture is to clear up responsibility. Who is to do what? To design the pattern of responsibility, we must not start with the question, who is responsible for quality? That is a non-question. It cannot be answered because it is directed at an abstraction, quality. What we must do is to break the question up into digestible pieces, into decisions and actions. Here is a proven method of approach. Convene the key people associated with a specific factory department. Ask them to identify the major quality-related decisions and actions for that department. Ask them also to identify who's available to make those decisions and take those actions. Then prepare a matrix like this. The horizontal rows are decisions and actions. The vertical columns show who is available to decide and act. Now give everyone a copy of the matrix and ask each of them to mark it up according to their views. Finally, transfer all the marks to one summary sheet. Let's follow the evolution of that summary. Here we see the views of Mr. A. He feels that the process should be set up by a setup specialist. He also feels that verification of this setup should be done redundantly by the setup specialist and by an inspector. Mr. A also feels that the process should be run by a worker, also that after running for 2 hours, the process should be re-verified by that same worker. As for the product made during those 2 hours, Mr. A feels the judgment of conformance should be done by the patrol inspector. That's one man's opinion. Now we have added the views of Miss B. She agrees with Mr. A in all respects but one. She feels that in this department there should be no setup specialists. The workers should be trained to set up their own machines. Now we have added the views of Mr. C. In some respects he agrees with A or B or both. In 2 respects he differs from both A and B. He sees no need for redundant setup verification. In addition, he prefers the judgment of product conformance be made by a different category of inspector. When all views have been posted to the diagram, what emerges is some unanimous agreements and some differences. The differences are then talked out and resolved. It is an easy do-it-yourself exercise. What made it easy was the fact that the non-question, who is responsible for quality, was broken up into digestible pieces. Systematic remedies are also available for the inspection and test phase of the spiral. Let's start with defect detection. Defect detection is a form of product inspection and test. It serves mainly to make decisions on the product. That is, does the product conform to standard? It also serves to make decisions on the process. That is, should the process run or stop? Defect detection is often done by inspectors or by production workers. These human defect detectors normally miss about 20% of the defects present. Such fallibility is unacceptable for critical and major defect types. However, we have many ingenious ways to minimize these human errors. If visual inspectors face large numbers of quality characteristics, we could provide masks to help the inspectors focus their attention. We can provide transparent overlays with boundary lines to facilitate judgment of conformance. We can provide templates to foolproof inspection for some types of characteristics. We can provide sense multipliers, optical magnifiers, sound magnifiers, alarm signals. We can provide aids to human memory. For example, physical samples to facilitate inspection by comparison. Judgments based on inspection by comparison are known to give greater consistency than judgments based on memory of what are the standards. A different approach is reorganization of work. The behavioral scientists advocate remedies such as job rotation, job enlargement, rest periods, and so forth. Military commanders have long debated what should be the maximum length of the watch for the lookout. Some commanders change the lookout every half hour during times of war. The ideal approach is to use non-human inspection and test to automate. This is widely done, especially for 100% non-destructive testing. To keep non-destructive test equipment in calibration still requires human technicians, but the trend is to automate the calibration as well. Now let's look at an important finding recently evolved with respect to human inspection or checking. Human inspection is done in two very different ways. Active checking, in which the very act of checking is what forces the checker to maintain attention. And secondly, passive checking, in which the checker is not forced to maintain attention. To illustrate, let's look at a check which is critical to human safety. In some blood donation centers, the red blood cells are returned to the donor after the plasma has been removed. Those red blood cells must go back to the original donor and to no one else. The system for assuring the identity of the donor includes the tubing through which the blood donation flowed from the donor to the collection bag. For each bag, the tubing is uniquely identified by an 8-character number, which is repeated over and over along the entire length of the tubing. At the time of checking, one nurse reads out loud the 8-character number on that segment of tubing still attached to the donor. The other nurse listens and then compares the number she heard with the number she sees on that segment of tubing still attached to the collection bag. The nurse who reads out loud is in an active state. To read out loud requires maintaining attention. The nurse who listens and looks is in a passive state. The actions of listening and looking do not require maintaining attention. It is feasible to put both nurses into an active state. For example, each could punch that 8-character number into keyboards which lead to a microcomputer. The computer could then give a signal, all clear, or alarm, while recording the numbers as punched. An example in office operations is that of verifying the accuracy of subscribers' listings for telephone directories. The listing includes the subscriber's name, occupation, address, phone number, and so on. The check consists of comparing the typewritten original with a proof of the printed version. Traditionally, the checking was passive. In the modern approach, the keyboard used to type the original copy simultaneously feeds the same data into a computer memory. Later, the checker, using the printer's proof as copy, punches the listing into a computer keyboard. The computer then compares the two inputs. This is active checking, because the punching cannot be done correctly without maintaining attention. Next, let's have a look at reducing the cost of inspection. Many high inspection costs are justified on the grounds that reducing inspection costs would allow high defect levels to escape. As we reduce the defect levels, we should follow through and reduce inspection costs as well. There are many ways to reduce inspection costs. Use sampling instead of sorting. If the chronic defect incidence has been reduced to a tolerable level, sorting can be replaced by sampling. Reduce the cost of sampling. Our published sampling tables usually assume that information about the lot must come solely from random sampling. This assumption is paid for by the high cost of large random samples. What we can do is to make use of other pertinent information, such as process capability and stability, sequence of manufacture. When we are able to use such added inputs, we are also able to use small, non-random stratified samples. Third, inspect closer to the source. Move the inspectors to where the product is made, rather than transporting the product to an inspection department location. Aside from cost reductions through improved logistics, the inspection becomes more precise due to improved traceability. Fourth, go to worker self-inspection. Under proper conditions, we can give workers the added job of product inspection. We then provide quality assurance through quality audits. Fifth, use prior test data. Arrange to secure reliable test data from vendors and other sources so as to avoid duplicating prior tests. Provide quality assurance by audit. The horizontal scale shows a sequence of shipments from a vendor. The vertical scale is quality. There's a maximum tolerance. The buyer has also arranged to receive the vendor's test data, shown on the graph by X. The buyer's test data are shown by circles. The first 6 shipments show that the vendor delivered product which conformed to specification. Second, that the vendor's laboratory made correct decisions. And third, that the test methods differ, but the vendor's test is more strict. Now the buyer reduces testing and relies increasingly on the vendor's test laboratory. However, the buyer retains an audit for added quality assurance. Sixth, optimize the economics. Evaluate the cost of finding a defect. Compare this with the cost of not finding the defect. Use the contrast to find the optimum level. Seventh, conduct value analysis. Compare the cost of finding a defect with the selling price of a unit of product and with the cost of a service call. Such figures are helpful for decision making. Eighth, challenge the standards, especially on sensory qualities. Discuss with industrial clients the needs of fitness for use and the costs of meeting those needs. Such dialogue helps to find the minimum total cost. For a consumer product, conduct market research to discover the levels of consumer sensitivity, tolerance, and intolerance. Finally, we can improve inspection work methods and productivity. conduct industrial engineering studies of inspection work to improve methods and establish standards of productivity. That's a long list. Now the high points of this session 13. Manufacturing planning should include early warning study of process capability. Manufacturing planning should include foolproofing. Foolproofing should include communications as well as hardware. Responsibility should be defined. Who is to do what? Human defect detection misses about 20% of the defects. Use active checking to minimize checking errors. As defect levels are reduced, follow through and reduce inspection costs. Between now and the next session, look back over prior improvement projects with which you've been associated. To what extent have these projects made use of systematic remedies in manufacture, in inspection and test? What are your conclusions? As to your current project, look to see whether systematic remedies are needed in manufacture, in inspection and test. Also, read the workbook notes for session 14. Good luck.